So you can program it to implement any combinatorial machine. But not probabilistic combinatorial machine. Okay, let's go to the next level. How do you get to the level of state machines? The idea is very simple. You split, and that's what electronic engineers use when they actually implement these devices. You split this table into two parts. One part describes inputs, A, B, C. Then the second and the third row will describe state and the next state. And the fourth row will describe what you retrieve. It's easy to show that any combinatorial machine can be implemented as state machine with the feedback. What is important to understand that you cannot simulate state machine with combinatorial machine. Because in this case, you have, depending on the state, you have two different combinatorial machines. So by switching state, you switch the system into different combinatorial machine system, okay? So now I jump to the highest level. How do you implement any universal computer? As Turing showed at some point, what is needed is just to add to that random access memory or tape. Okay? So, well, I will skip that. I have this PowerPoint which we will be able to read. So anyway, there is a deep actually reason why you cannot implement something of higher level with the lower level. Because you always get combinatorial explosion. You try to implement, say, state machine, assuming, say, limiting the length of the input sequences and mapping that as combinatorial machine, and you get explosion because the size of prom grows as x to the power of n. And if you want to implement this universal computer using state machine, though it is state machine, it again, the size of tape produces so many different states that it explodes combinatorially. So really, it's not the reason that it's kind of theoretically you cannot implement. The problem comes much earlier in the form of this combinatorial explosion. Okay, I hope. Okay, let's now kind of, this was a little boring maybe, but let's now apply that to the brain. Let's make this observation. A person with a sufficiently large external memory aid can perform in principle any computational procedure. That's how Alan Turing invented his machine. He assumed that no system can calculate more than a person with a big memory. And then he decided to reduce this machine to the simplest possible form without losing this ability to compute what person computes. Okay, I skip other observations, and I go directly to kind of my vision of Turing machine. You can think of Turing machine as a robot which calculates on the tape. And to make it more kind of human-like, I introduced I, which reads single symbol from the tape. I introduced speech, which robot talks to itself. It tells what next state he wants. And I introduced this, what Turing machine requires, write symbol and move. Okay? So this robot is a Turing machine. But it really gives you kind of robot-like interpretation of Turing machine. Let's go one step further and ask the question, what is the brain? Suppose I'm serious about that. Which means, okay, Turing took a person, reduced the person to the level of robot, and invented, it made this most prominent discovery. He invented universal computer. Let's go in the opposite direction. Start with the robot and gradually build it back into a human. So the Turing machine is a good place to start because it's already universal, which means we don't have all this problem of not having enough computing power, which you will see a big problem with the brain. We take universality for granted because in computers we have more, in all our computers, we have more than enough resources to get universality. But it doesn't buy you principal advantages, it buys you only efficiency. You don't get combinatorial explosion, say, if you describe this laptop in terms of Turing machine, which is essential. So how do I implement it as a, what kind of brain? And here I show the simple brain. Well, these are neurons, big circles, and small circles are synapses. So it's very similar to this programmable logic array, except that this layer, intermediate layer N2, these neurons would compete, so they would select a single line, a single associations, let's call it, randomly. And they will select associations with the highest level of excitation. So I don't have time to go into the theory of that, but there is exact theory of that which is absolutely explicit, so whatever I say can be proven either theoretically or computer simulation. In fact, I have a program which simulates it. Okay, so this is sufficient to get the robot, universal learning robot, in a sense, with this very simple concept of learning. So how do I teach this robot? Suppose I have control of the robot motor centers. I plug these electrodes, and now I can make this robot do whatever I want from teacher, right? So I can force it to compute. What I want, that after I finished several examples, this robot would learn to do any examples from this algorithm. Is it possible? Yes. In this very simple way, it is possible. And okay, so, but I want to get rid of the neural network, so I actually go to what you need are 3 procedures: decoding, then choice, and encoding. And these 3 procedures, if you can implement them efficiently, you can build the robot which I described you, which would be able. Also, you need some kind of procedure of learning, which means how data would be stored in the robot's memory. And then this robot simply tape record the data, which means it simply records these signals in the memory, which means it just records all the input signals in this upper part of this network and the output signals in the lower part of the network, in the synapses, and that is sufficient to actually learn anything. Okay, so let's go and ask more difficult question. Suppose I want this robot to do mental computations. That here I come to the problem of working memory and mental imagery. Suppose I want to build a robot which would do the following. Like, once I showed it several computations on tape, it would be able to mentally simulate this external system. Do you remember I was talking about this right part of that? How the world, how tape is seen through the robot devices. So how can you make this happen? Because I claim that the brain doesn't have random access memory. There is no room in these networks for random access memory, and this is a very kind of important claim, which means somehow you need to reach universality without having a memory buffer. Imagine how many of the traditional algorithms would survive this limitation. You probably would have to drop all traditional artificial intelligence algorithms if you are not allowed to move data into RAM buffer. So how can brain still do that? Okay, so let's now, so this is my problem now. So I want this system, let's assume that there are two systems in the brain. One system which does motor control, the one which moves robots, which speaks, which moves robots, hand to right. Another which simulates this external system, the external world, in this case, tape, as it is seen through these devices. Can I arrange this system in the same way as the previous system? Well, yes, I can, but I need, so this is kind of my final robot. I want this robot to do the following. If I force it to compute, it then will learn not only to compute on tape, but it will also learn to compute mentally. And this is a kind of implementation of this robot. So there are two systems, and they are represented as tables. All the machinery is kind of skipped, but I have description of this algorithm in one of my papers, and also I have references in the PowerPoint which will be available. Okay, so let us, and I can force this robot to do anything by actually typing symbols here. So because I don't have time, I'll just show you some examples of this training. In this case, the robot was trained to do so-called parenthesis checker algorithm. It needs to determine whether for any left parenthesis there is a matching right parenthesis. There is a simple Turing machine algorithm which does that. So I actually forced the robot to do 3 examples. I showed it by forcing. And that is what is in robot's memory after that. Okay. Now, what I will do, robot now looks at the tape. You see there is this little kind of switch memory tape in the upper part. So robot looks at the tape. So it reads this data. It reads this data, then it turns and it opens the eye, so it it closes the eye. So now it will see everything from the memory only. It still goes and computes, which means without actually memory buffer, it computes and it learns to compute, and it will do perfectly well with this algorithm. So what happened? The robot learned. I showed the robot how to do few computations, and now it is capable of doing any computations from this class. How is it done, actually? Let me close this. So I just showed it, because it's a big topic, so probably don't have enough. Okay, the only thing you need, if you don't have memory buffer, you need to introduce this analog memory, and it is plentiful. It is available in the form of so-called neuromodulation. So suppose you have this neural network. Do you remember there was 3-layer neural network? So the only thing I need to add to that is this modulation, which means when the robot, or whatever, when this network receives the signal, the level of excitation, of residual excitation in this location is higher. So it creates this bias. Okay, so this description, I will not go through this, you can understand it. But let me explain how it actually achieved. It is achieved through the effect of recency. Imagine that you bias this table, which means you have, in the upper part, you have, for example, this association, 3 is associated with A, 3 is associated